In our last video, we talked about direct proofs of if-then theorems, and our first topic for today is to extend that to if and only if statements. The notation for if and only if is a bidirectional version of the if-then arrow. And this indicates that A, if and only if B, is a combination of if A, then B, and if B, then A. Let's look at an example of a simple if and only if statement to give a bit more context. The statement x is even if and only if x plus 1 is odd is saying if x is even, then x plus 1 is odd, and if x plus 1 is odd, then x is even. We'll also sometimes use the phrasing A is true exactly when B is true, and we'll often abbreviate if and only if using an if with two F's. And because an if and only if statement requires the implication to be true in both directions, it's equivalent to say A if and only if B, or B if and only if A. And just like last time, we can make a table of the individual truth status of the statements A and B, and look at the overall truth status of the statement A if and only if B that results. One handy way to think about this table for if and only if is in terms of the exactly when phrasing, that the statement A if and only if B is true when A and B are true at exactly the same times. So that would mean that the if and only if statement is true if A and B have the same truth value, but it's false if they have different truth values. Another way to think about this is that for the if and only if to be true, we need both A implies B and B implies A to be true. A implies B is true in the first, third, and fourth rows of this table, as we saw last time. But B implies A, the case where it's false is when B is true and A is false, which is the third row of the table. And so they are both true only in the top and bottom rows. So how do we prove an if and only if theorem? Well, we have our second proof template of the semester for that, and we will use this statement as an example that we can prove to show off the template. The template here is a straightforward one. We are breaking the if and only if statement down into the two if-then directions that make it up. And then we can prove each of these directions separately using whatever proof template we like for an if-then theorem. Right now, we have proof template 1 for if-then theorems, but we'll have more options available soon. When you're writing up the statement of a theorem for your homework, I recommend writing it out fully in English, like this example, but there are times when abbreviating with symbols is more handy. So, using our proof template 2, we have two pieces we need to prove. First, the if direction, and then the only if direction. So for this statement, the forward direction would be x is even implies x plus 1 is odd. And the reverse direction would be that if x plus 1 is odd, then x is even. So now we have two if-then statements, and we can approach each of them with our proof template from last time. We start with our hypothesis at the top and our conclusion at the bottom. Now we unravel definitions. And now that we've unraveled both definitions, we can just add one to both sides to make them the same. And we've completed the template 1 proof of our first if-then component. So now we can prove the other direction. Again, we'll start with our hypothesis at the top. And our conclusion at the bottom. And now we see that exactly the same pattern that gave us the forward direction will give us the reverse direction here. And here, since we already see where we're going, we notice that we don't even need to unravel the conclusion, and just getting to x equals 2a shows that x must be even. So now that we have proven both the forward and reverse implications, we have completed our proof of the if and only if statement. So between the last video and this one, we have a couple of different templates for proving our conjectures, but I told you last time that being able to disprove a conjecture is just as valuable as being able to prove it, so we should talk about how we go about disproving things. To disprove the sort of conjectures that we've seen so far, it helps to observe that all of our conjectures to this point have implicitly contained the word all. For example, our hypothetical conjecture based on generating random prime numbers was that all prime numbers are odd, and one of the statements we just proved is saying that all even integers have an odd integer above them. For statements like these, where we are saying that if an integer is prime, then it is odd, or if an integer is even, then that number plus 1 is odd, we are saying that for every number where the hypothesis holds, then the conclusion also holds. So to disprove these sorts of conjectures, it is sufficient to give a single example where the hypothesis is true, but the conclusion is false. So for the first conjecture, 2 is a counterexample, which means that this statement is false. And for this second statement, well, we just proved it to be true, and so if there were a single counterexample, it would be false, so we know that there must be no counterexamples to this statement. So for these examples, we know whether they are true or false, but let's go back to our example where we're not sure. So the claim is, if it rains, then I bring an umbrella. So to disprove this statement, all we need is a single counterexample where the hypothesis is true, but the conclusion is false. So you could refute my claim with the single counterexample that yesterday it rained and you saw me without an umbrella. So this brings us to our third proof template based on exactly this idea. We've already seen a couple of cases of counterexamples in action, but a common occurrence is that you have a claim and you don't know whether it's true and you should be trying to prove it, or whether it's false and you should be trying to find a counterexample. And so I'll find that what often happens to me is that I'll have a conjecture and I'll try to think of a counterexample. I'll think through a few examples, and each of those examples turns out to work. And so after failing to come up with a counterexample, my next approach might be, okay, I'll try to prove my conjecture and turn it into a theorem. But then when I start working on a proof, sometimes I'll succeed, but other times I'll get stuck, and a decent fraction of the time, when I get stuck, that will actually help me to build a counterexample that I can use to refute the conjecture. The section of the textbook that is assigned reading for today gives a great example of this, and I'd like to go through that example to give you a sense of this process. So our conjecture here is that if we have two integers that each divide the other, then those must be the same integer. And let's suppose that you're not sure whether this conjecture is true. Maybe you've thought through all of the factors of 12, and the only one that divides 12 is 12 itself. So this is kind of making sense. And now you set out to prove the conjecture. This is an if-then conjecture, so we can try to show it with proof template 1. And we'll write our hypothesis at the top and our conclusion at the bottom. And now we can start unraveling the definitions. A divides B and B divides A. So there's some integer x that we can multiply by A in order to get B. And there must also be an integer that we can multiply by B to get A. And now we could substitute B times Y in for A. And now we can simplify, dividing by B. And so now we have two integers x and y that multiply to give us 1. And, well, if x and y are both 1, then A is equal to B. But at this point, it's clear that there's another way to multiply two integers and get 1. X and y could both be minus 1. So now to complete our proof, we would need to consider both of these cases. In the first case, it does work out that A equals B, but in the second case, if A times minus 1 equals B, then that means that A equals minus B. And so this gives us an idea for a counterexample. So we realize that if A is equal to minus B, then they divide each other, but they are not equal. And so we have a counterexample where the hypothesis holds, but the conclusion doesn't. And so we conclude that our conjecture was false. So an important takeaway here is that in many of your classes, you probably know whether you are trying to prove a thing or disprove a thing. But sometimes when you're doing math, you will have a conjecture and you won't know whether that conjecture is true or false. And so in those cases, it's good to switch back and forth between looking for a counterexample and trying to prove it. And those two efforts can often help each other. By thinking about the proof, you might come up with a counterexample, or by looking for counterexamples and thinking about why it isn't working, you might help yourself come up with a proof.